not actually sure if this sliding is any better, but whatever, doesn't really matter. Okay, so today we're moving on to section 2.2 in your book. We're going to cover the entire section today during this lecture, but this is mostly just basic isolating variable stuff. Shouldn't be too terribly difficult, I hope. We are going to go over a couple of different ways to solve these instead of just using the symbolic or mathematical representations. We'll go over graphic and numerical as well. But it shouldn't be too difficult, I don't think. Most of this is going to be reviewed for you guys, but we're going to start with linear equations. So we know that a linear function looks at the effect of our input variable, which is our x, on our output variable, y. So as x changes left to right, you're having some kind of change in y, and it's either positive, negative, horizontal. Vertical is not a function, but close enough. It's also something that, well, you can graph and will be linear. But linear equations look at a single variable rather than more than one. And so basically, these kinds of equations can be written or simplified to ax plus b equals 0. So a linear equation, we'll talk about identifying and linear and nonlinear equations. So before we can start solving these as linear equations, or at least before we can determine that they are linear equations, we need to be able to identify linear and nonlinear equations. So the easiest way to do this is to look at your variable. Usually that's going to be an x, but you can have an a, b, whatever. It doesn't really matter. Generally, it's going to be an x just because that way, if you put it into y equals mx plus b form, you can graph it that way. If x is raised to any power, including fractional powers like square roots, so square root is the power of 1/2. This does seem a little bit weird, but anyway, let's try that. So including fractional powers like square roots, cube roots, negative powers, anything like that, you're going to have a nonlinear equation. But if the x is not raised to a power, the equation is most likely linear. So let's try some practice with these ones. So x plus 3 equals 12. We can rewrite this as 1x plus, and then actually it's going to be minus 1x minus 9 if we subtract from both sides equals 0. So since we can write that in ax plus b equals 0 form, that is linear. The next one, 2x squared. This x is squared, so we know that this is not linear. So linear, non-linear. Square root of x, this is the same as x to the 1/2. That's a fractional power, so this is non-linear. This one, x minus 3 equals 2x plus 12. If we simplify this, we can subtract x from both sides, and then we can add 3 to both sides, and we'll get x plus 12 equals 0. So this is also linear, and I think x equals 6. So this obviously we should know is a vertical line if it's our previous one, but you can resolve that as x minus 6 equals 0. So that is also linear. Okay, hopefully that makes some sense. You're just looking for an x by itself without a square or a square root or an e to the x or something like that. So to solve linear equations, basically you're just isolating the variables. This is something you've probably seen before, but we'll look at a few different ways. So let's start with this one. We want to solve this for x. So obviously the first thing we want to do is add 6 to both sides. So we get 3x equals 15. Divide both sides by 3. And we get x equals 5. So hopefully you guys know the basics of how to isolate variables by this point. You work through reverse order of operations. So so you want to kind of work back this way when you're solving linear equations, but it kind of depends on the actual problem itself. So one of the things to be careful about when doing linear equations, this is a mistake that students make all the time, is when you get something like this, 3x minus 5 plus 12, you have to make sure to use the distributive property. So this goes to this and it goes to this minus 5. It goes to both. So when you write this out, it's not 3x minus 5 plus 12. It's 3x minus 15 plus 12 equals 0. And that's just because of the distributive property. So then when you solve this out, we'd have 3x minus 3 equals 0. So x equals 1. You could add 3 to both sides and then divide by 3 to get x equals 1. I just kind of skipped a couple steps at the end there. So another one that leads to a common mistake is this one, 5 minus 3x plus 2. This negative sign is effectively the same as doing 5 plus negative 1 times 3x plus 2. So we need to distribute this negative as well. So it goes to both the x and the plus 2, even though it's just minus. So for instance, we would get, in this case, 5 minus 3x minus 2 equals 4. We solve this, we get what? 3 minus 3x equals 4. 3x, negative 3x equals 1. X equals negative 1/3. Okay, so hopefully the basics of all of that are things that you remember. Let's look at some more complex linear equations. So something like this. We have 3x minus 2 equals 2x plus 4. So the simple way to solve this, obviously, is to isolate your variables by moving this over, add 2, and then that's actually because 3x minus 2x is 1, minus 2 plus 2, these cancel, 2x minus 2x, these cancel, 4x plus 2 equals 6, so we get 1x equals 6, x equals 6. So the key on this one is just generally you want your bigger x value to be the one that stays, and you could subtract the other one from the other side. This one is a significantly more complicated problem. Students struggle with this kind of thing quite a bit, actually. This is one of the ones that's more difficult for most people to solve. The easiest way to do this is to just multiply everything out by the least common denominator of your fractions. And then solve from there. So in this case, you have 9 and 5. The least common denominator of 9 and 5, 9 and 5 is 45. So we want to multiply everything in our equation on both sides by 45, which will give us 5x. So you have 45 over 9, 45x over 9. This is 5x. And then you'd have 45x over 5, which equals 9x. So 5x plus 9x minus 45, because 45 times minus 1 equals, and then we've got 45 over 9 is 5, so 5 times 5, we have 25 on this side. So we add 45 to both sides. We get 14x equals 70, and then that means that x equals 5. And you can plug that back in and check. So you'd have 5 over 9 plus 5 over 5 minus 1 equals 5 over 9. And since obviously this is plus 1, this is minus 1, these cancel out. You have 5 9s equals 5 9s, which is correct. Okay. So another thing to watch out for when you're solving linear equations is contradictions and identities. So there are some linear equations that are going to turn out to always be false. So if we solve this, we have 7 plus 6x equals 2 times 3x plus 1. We multiply this out, and we're left with 7 plus 6x equals 6x plus 2. If we subtract 6x from both sides, these all cancel, and we're left with 7 equals 2. So if we solve this, we end up with 7 equals 2. This is not a true statement, so this linear equation is a contradiction. This statement right here is unsolvable. It is incorrect. The opposite, the identities version. So this is 2 times 5 minus x minus 25 equals 3 times x minus 5 minus 5x. If we solve this out, we get 10 minus 2x minus 25 equals 3x minus 15 minus 5x. We simplify both sides. 10 minus 25 is negative 15 minus 2x. equals, and then we've got 3x minus 5x, that's minus 2x. This is negative 15, so negative 15 minus 2x. These are the same, right? We could solve these out. We could add 15 to both sides and add 2x to both sides, and we would end up with 0 equals 0. So if we solve this out, we end up getting 0 equals 0 right here. And this statement is always true. So this equation is an identity. These are basically the exact same things. They're just written in different ways. Neither of these types of linear equations are particularly useful for anything. This is basically like saying 0 equals 0. Everybody already knows that. That is a fact. And this is basically just wrong. So neither one of these linear equations really helps you for anything, but they will come up occasionally, and you should be able to identify them if possible. So hopefully all of the solving mathematically things are things you've practiced before, you've done plenty of times. I don't really want to go into too much detail on that. If you need help with these, if you need extra practice, you're going to get some practice in your homework, but if you need extra clarification, work with me and I can help you. Make sure you've got the algebra skills to be able to solve those. But we're going to look at a couple of other ways to solve linear equations. Specifically, we're going to look at graphically and numerically. So graphically, first of all, use your graphing calculator for it. It's going to be a lot easier than trying to graph everything by hand. But whoa, this jumped kind of forward faster than I expected. So you can solve linear equations by graphing them on your calculator. So we've got 2x plus 1 equals negative x plus 4. Now we could just solve this. It wouldn't be too terribly difficult. But solving it on a graphing calculator, what we want to do is treat each of these like its own linear function. So you're going to graph y1 equals 2x plus 1, that's this side, and y2 equals negative x plus 4, that's this side. The x-coordinate of the points at which these two lines intersect will be the answer. So if you go ahead and graph this on your graphing calculator right now, plug those in, and then you'll see they intersect at the point 1, 3. Right, so we've got 1, 3. 1 is our x, so the solution is x equals 1. Now, we can really easily check this by plugging 1 in for x on both sides. If we plug 1 in here, we get 2 times 1, which is 2, plus 1. That's equal to 3. So this side would equal 3. And if we have negative 1 plus 4, 4 minus 1 is also 3. 3 equals 3. That's a check. So we know that this is the correct way of doing this. I don't have any way to show you on the graphing calculator right now, but this is, you just go into your y equals, you plug in 2x plus 1, negative x plus 4, and you can solve for those. Another way to do it is the Xintercept method. So in order to do the Xintercept method, you first need to simplify your linear equation to equal 0. So for instance, you could simplify to get this, 3x plus 22 equals 0. Then you graph this, y equals 3x plus 22. And then whatever the x-coordinate of your x-intercept is, so remember the x-intercept is when you have x, comma, 0, y equals 0. That's going to be the answer to this equation here, which you can see because, this is supposed to be y equals 0, so y should equal 0. This will give us our x. In this case, that's like, what, negative 7 1/3, I think. But yeah. And for graphing calculators, since it is really difficult for me to show you how to use them online and stuff, if you have questions about graphing calculators, please email them to me and I'll start compiling a list of like YouTube help videos that I can suggest to you guys for various different things. But hopefully you know how to graph y equals 3x plus 22, and then you should be able to just move along the line until you find the x-intercept. So to solve numerically, remember that numerical answers to things look like this: x, f of x, and then you've got a bunch of different, like 1, 2, 2, 6, 3, 10, etc., right? And these go on and on and on. Yeah. So solving numerically, for this, all we do is simply make a chart of values for x and your function. So 2x minus 1 equals 3. So what we do here, we have x, then 2x minus 1, and we look for where 2x minus 1 is equal to 3, which is here, right? And so that means that this is our x value at our solution. One of the nice things about doing this numerically is, like, let's say you had 2x minus 1 equals, let's say it was 2, right? Like if you wanted this to be your answer. What you would do is when you see this, you can look and see, okay, well, at x equals 1, our the value is 1, and at x equals 2, our value is 3, which means you know that it's somewhere in between these 2 points, some kind of fraction or decimal, so you can look in between two. So that's one of the nice things about doing numerically, but it also means you have to do a few more calculations, so it can also be a little bit more complex. Your graphing calculator should be able to give you these tables as well if you just plug in the y equals 2x minus 1. Plug that in to your graphing calculator, you should be able to find the table of values, and then you can use that to solve for it as well. No matter what method you use to solve a linear equation, your answer should be the same. So if you solve it graphically using the Xintercept method, and you solve it numerically using a table, you should get the same answer. If you solve it symbolically and solve it graphically using the intersecting lines method, you should get the same answer. The only difference is that answers may be rounded slightly in graphical or numerical solutions. So in things where you plug them into your calculator, it might give you approximations if the number is really, really complex. Whereas if you solve it numerically, you can get exact answers most of the time, or symbolically, sorry. So similar to how you would solve an equation for x, you should be able to solve linear equations for a variable. So basically, this is just simplifying an equation. This is kind of a mathematical process thing more than it is a linear equations issue. But let's look at an example of what I'm talking about here. So this is the area of a trapezoid. It's 1/2 h times the top base and the bottom base, which in this case we're representing with a plus b. So in this case, we want to solve this equation for b. You should be able to, even though these are all variables and there's only one real number in it, you should be able to solve this for b. So in order to do that, let's look at how. First step we want to do is multiply both sides by 2. So now we have 2a equals h times a plus b. Then we need to divide both sides by h. So 2a over h equals a plus b, which means we have b equals 2a over h minus a. So you should be able to do something like this. Obviously, this doesn't really do anything for us right now. We can't solve this, but if we were given a trapezoid, we were given the area of the trapezoid, the height, and just one of the bases a, we could solve for the other one, much like this. So this is just a simple procedural thing that you guys should be able to do at this point. If you're confused about how to do stuff like this is also one that you're going to want to talk to me about. This is kind of one of the things that the textbook and the class kind of assumes you've seen before and know how to do. So if this doesn't make sense to you, or if this is difficult for you, please talk to me and we'll work on getting you caught up on that. The other thing that your textbook thinks is really important at this point, and I'm really not sure why they think this is necessary in a what's effectively a pre-calculus class, but converting percentages to decimals and vice versa. I really hope everybody knows how to do this by this point, but a number as a percent, so we have that as capital R percent, is equal to 100 times the number as a decimal. Converting from a percent to a decimal, really hopefully you guys know how to do this by now. 37% is 0.37, 4%, 0.04, 0.5%. Now this is one that students do mess up. This is a mistake that happens, and I understand where this one comes from, but that is equal to 0.005. So if you have a percent, here, let's do this. If you have x percent, then x as a decimal is x over 100. If you have a decimal, 0.x times 100 equals x percent. Right, so that hopefully is review for you guys. I hope that everybody knows how to do this at this point. But your book thought it was important to talk about, so I went ahead and threw it in here kind of last minute. Go ahead and get to work on the assignment for this one. Also has a lot more optional problems than it has required ones, but please go ahead and work on those. Write down any problems you have problems or trouble with, anything that you want to go over in class or ask me questions about. I can hopefully help you with there. But you do want to know how to do this solving linear equations and solving for single variable equations before we get into what we're doing tomorrow, which is inequalities. But that is it for today. So I'll see you guys later.